Hello, and welcome to the video accompaniment for Chapter 8, Section 3 of our text. In this one, we're talking about the pigeonhole principle. So the first three sections of this chapter, Introduction to Counting, are all principles that tell us how to solve certain set problems, counting problems. And so we'll encounter another one here. By the end of this, you'll be able to apply one of the forms of the pigeonhole principle, and there are a couple different forms, to solve some problems related to set structures, and then to be able to take those abstract things and apply them to some story problems, some real-world scenarios. In this video, we're going to show that the pigeonhole principle is true, so we'll actually prove it, and then we'll explore and prove some generalizations and variations of the principle, so things that are asking similar questions but are a little bit different. So just like the other counting principles, I like to start with a motivating example to get to the principle. So this is going to deal with the board game Risk. So maybe some of you have played this before, maybe some haven't. I'll sort of explain it in a minute here. What Risk is, it's a game where you try and conquer other territories, right? It's a big map of the Earth, split up into countries and territories, and you control some of those, and you want to expand your territories. You want to conquer other people's territories. So every turn, you get to try and conquer someone else's territories by rolling a dice, etc. Now, if you are able to take someone else's territory on a turn, then you get a card. Drawn randomly from a deck. And in the deck, so each card in the deck either has a picture of a soldier, a horse, or a cannon on it. And the deal is that if you get three cards of the same type of card, so either three soldiers, three horses, or three cannons, then you can turn those cards in and get some troops for your war effort. Now, it's not always advantageous for the player to turn in as soon as they have three of the same card. However, the rules state that as soon as you have three of the same type of card, you have to turn in. Now this is, by the way, this is a modification of the rules. This isn't quite exactly the rules of Risk, but just go along with me. There's also like a wild card, and you can turn in when you have three. What's the question here? So the question is, what's the smallest number of cards a player must hold in their hands to guarantee that they have to turn in? So this would be the number of cards such that if you saw someone else with that number of cards, you know that they have to turn in. And so you could, if they didn't turn in, you could point at them and say, hey, you're holding out, you have to turn in. I know that you have three of the same type of card. So what is the smallest number of cards someone has to hold? So questions like this are answered by the pigeonhole principle. So let's just try and solve this outright before we know the principle. So there are three types of cards, right? It can either be a soldier card, a horse card, or a cannon card. I'm going to think of these types of cards as like bins. And then I'm going to fill these bins with objects, and where are the objects? The objects are cards. So let's say I have three cards in my hand. So here's my hand up here. Let's say I have three cards. Am I guaranteed to have three of the same type of card? Well, the key here is guaranteed. Am I guaranteed? No, I'm not. I could have a soldier, a horse, and a cannon. So I'm not guaranteed. Right? It's possible I have all soldier cards. That certainly is possible that I have this configuration, but that's not the question that's being asked. What's being asked is, how many cards do I need to have to guarantee three of the same type? And so in all cases, you would have to have three of the same type. So three doesn't work. We just showed three doesn't work because there are configurations that avoid three of any kind. So what if I had four? Well, how can I do that? Well, again, I could have one soldier, one horse, one cannon, and maybe, I don't know, another cannon. I still don't have three of any one type. So maybe I need to have another one. Well, I could put that into a horse. Maybe I had another one, I could have a soldier. But then it seems if I have this next one, that no matter how I do it, I'm going to have three of the same type of card. So why is this? Well, suppose I claim 7 is the number. I claim seven cards. And why do I claim this? Well, let's assume to the contrary that we can do such a configuration where each type of card, there's at most 2 of each type of card. Okay, so that means as I'm assigning these cards to type of card, I can only have at most 2 of any one type. So that means maybe these 2 are both soldiers, these 2 are horses, these 2 are cannons. At most 2 of every type. And so if I have that, then where does this 7th one go? It can't go to any of them. Otherwise, I'll have 3 of one type. But it has to. So therefore, I do have 3 of one type. So that's the sort of argument that the pigeonhole principle is stating, that we're in this sort of situation, and this is gonna deal with. Notice where this number came from is that if I take 7 over 3 and I take the ceiling of that number, that is 2 1/3, so the ceiling would be 3. That this is the number of that I have 7 objects split into 3 categories. How many am I guaranteed to be in any one category? That's the answer here, 3. This is how many I'm guaranteed to have in some category. All right, let's see it stated. So the pigeonhole principle says this: if we have a set S with n elements and it's divided into k pairwise disjoint subsets, S1 through Sk, then at least one of these subsets has at least a ceiling of n over k elements in it. So this is very general, more general than we had before. So I have this example. Here I have a collection of pigeons. I have 7 pigeons and I have 3 holes. Black holes, because why not? Let's put pigeons in black holes. Really what's being referred to in the pigeonhole principle are these drawers in desks. They used to be called pigeonholes. And in German, this is called the drawer principle. But since it's called pigeonhole, I'm going to take pigeons and put them in black holes because we got to have some fun. So the set of pigeons, that's my S. And it has n elements in it. Or in general, it'll have n elements in it. In this case, we have 7. 7 elements. So n is 7 here. That's the number of pigeons. And it's divided into k pairwise disjoint subsets. So that means I'm going to partition my pigeons, and I'm going to put each one in each pigeon in exactly 1 black hole here, in exactly 1 subset. So these are my subsets down here. I'll think of this like S1, S2, and S3. So that means my k, that's the number of holes, would be 3 here. And so let me go ahead and compute a ceiling of n over 3. We did this in the last one, right? This is 3. And so this pigeonhole principle says in this case that one of these black holes, at least one of the black holes, has at least 3 pigeons in it. In any assignment, no matter what the assignment is, I'm guaranteed at least 3 pigeons in at least one of these sets, in at least one of these black holes. So right, it's the same argument as last time. Suppose none of them have at least 3 elements in them. Then they all have at most 2 elements in them, right? So this is sort of maxed out. I would have at most 2, at most 2. And then when I do this, right? So I assign them. Oh, 2 there, 2 there, 2 there, and then where does the third one go? One of them has to have greater than 3 elements. So this would be an example of a contradiction, and this is how we're going to prove it. All right, let's actually prove the pigeonhole principle. All right, so it's a big implication. If a set S with n elements is divided into k pairwise disjoint subsets, then at least one of these subsets has at least ceiling of n over k elements. So what I'd like to do is assume the opposite of this. So we have, right, so remember this is like P implies Q, where P is if a set has n elements and it's divided into k with pairwise disjoint subsets, S1 through Sk, Q would be at least one of these subsets has at least a ceiling of n over k elements on it. And then the negation of that, so because I'm gonna try a contrapositive here, would be P and not Q. So what are my assumptions? My assumptions are that we have the set split into k pairwise disjoint subsets, and that none of them, so this is at least one of these subsets, so that means there exists a subset that has at least ceiling of n over k elements on it. So that means my negation of this part, my not q, is going to be for all, right? So the top one was there exists a subset with greater than or equal to n over k elements. Let's get that clear. And then the negation of that would be, so what if I want to negate this, would be for all subsets, we have their cardinality is less than n over k. That would be my assumption. So like in the last one, that's the bit where I get to say that, well, then none of them have, or that they're all less than 3 elements in each one. And in that case, I could say, because we know they're integers, that it was actually less than or equal to 2. So I'd like to do something like that here. In fact, sorry, this is cardinality. Cardinality less than n over k. So in fact, let me go ahead and write proof. We're really getting going on this proof. Oh, that's not the right yellow. I want this one. So we'll assume that each of the sets has cardinality less than ceiling of n over k. So assume S sub I has cardinality less than n over k for each I. That has to be true for all of them. And then I'd like to say that's less than or equal to the next integer down. And so what I can say there actually is that, so since S sub I is an integer, what we actually have is that S sub I is less than or equal to 1 less than the ceiling of n over k, right? If it's strictly less than ceiling of n over k, it's going to be less than or equal to ceiling of n over k minus 1, right? So if n over k is like, I don't know, 3.7, in order to be less than 3.7, you have to be ceiling of n, or so n over k would be 3.7, ceiling would be 4. And if I want to be less than 4, I have to be less than or equal to 3, which is 4 minus 1. And even if n over k is an integer, like let's say n over k is 7, ceiling of that's still 7, and S sub I has to be, cardinality of that has to be strictly less than 7, which means it's less than or equal to 6, 1 less than 7. So this should work. I've sort of explained my way through that in words. I'll just write it down. If you want, you can look at the book, which proves that with a little bit more detail. And then what happens if I add all of these up? Then I know if I add them all up, since this is really a partition, right? We've divided our set into k pairwise disjoint subsets. So we've partitioned our set. That means that when I add up all of the cardinalities of the S sub i's, I should get n, right? So n is the sum of the cardinalities of the S sub I, and this sums over all of the sets, so I equals 1 to k. I know that each one of these, is less than or equal to this ceiling, less than or equal to ceiling n over k minus 1. And then, so I'd like to say actually that, so I'll put this up here because I want to bound on this. They're all this. I'd like to say that this is less than something involving n over k. And so this is also true, that the ceiling of n over k minus 1 is strictly less than actually n over k. So this will be true in all cases. Again, you can look at the book for a little more detail on why that's true, but just kind of think of it for some examples. Think of when n over k is some fraction, and then think of it when it's an integer, and it'll work in all cases. And so what I can say then is this is strictly less than the sum from I equals 1 to k of n over k. Well, what happens when I sum up n divided by k? Right, this doesn't depend on I. So this is really just n over k plus n over k plus n over k, k times. Well, that's the same thing as k times n over k, and that's n. So what do we have here? We have that n is less than n. That's nonsense. That's a contradiction. A contradiction. And that proves it. That proves the Pigeonhole Principle. So let's see this in action in a couple more examples. All right, so let's take a look at an example. Let's say a teacher assigns each of their 42 students one of the letter grades A, B, C, D, and E. How many students must be assigned the same grade? All right, so think of the students as pigeons. There's 42 pigeons, and how many holes, how many different categories can they go into? 1, 2, 3, 4, 5. So the Pigeonhole Principle says take 42, divide it by 5, and take the ceiling of that. So this would be, what, 8.4, so take the ceiling of that, that's 9. And so the Pigeonhole Principle then tells us that at least 9 students all have the same grade. We can't say for sure which grade it is. This is just telling us at least 9 share the same grade. Notice, right, again, we can't guarantee that 9 students will get an A. We can't guarantee 9 students will get any particular grade. What if the teacher gives their student all Fs? Then no one has an A. However, there would be at least 9 students that had an F in that case. And that's true in general, right? There will always be at least 9 students that share the same grade. It's pretty cool that this works out. Let's see another example. So I have this bowl of change that's sitting on my desk right now. It contains a lot of different kinds of coins, let's say at least 11 of each kind of coin. And what are the kinds of coins? I have pennies, I have nickels, I have dimes, and I have quarters that are in the bowl. And let's say I pull 10 coins out at random from the bowl. How many coins am I guaranteed of the same denomination? Well, this is, again, a straightforward application of the Pigeonhole Principle. So I have my set S, my pigeons, are these 10 coins. And each one can be one of 1, 2, 3, 4 different kinds of categories. So like my N would be 10. If you like to think of it like this, assigning variables, N is 10, and K is how many categories I have, 4. And so the Pigeonhole Principle tells me that there are ceiling of 10 over 4, which is 3 of the same kind. That no matter how I did that, in any situation, I would have at least 3 of the same kind. Again, I can't guarantee any particular kind, can't tell you what it is, but there'll definitely be 3 of the same kind in there. All right, let's take a look at a slightly different question. All right, slightly different question I can ask that's related to this is this: what is the smallest number of cards? So, oh yeah, back to the example before. What's the smallest number of cards a player must hold in their hands to guarantee they must turn in? Right, when we solved this one, we could see sort of at the end that 7 over 3, right? Our answer was 3 because the ceiling of 7 over 3 was 3. And the Pigeonhole Principle then would say, right, so if we had 7 cards, then 3 would have to be of the same type. But that wasn't what the question was asking, right? It was, what's the smallest number of cards we needed? So it wasn't asking how many would be of the same type. We knew how many had to be of the same type, right? 3 of the same type. And we wanted to find this number, 7. So it's sort of the inverse problem. So what is this number in general? So that is, if I give you positive integers r and k, what's the smallest cardinality of a set n, or smallest cardinality n of a set S, such that if S is divided into k subsets, then at least one of these subsets has at least r elements. All right. So this is a huge mouthful, but this is just like the question that was asked in the last one. So given positive integers r, so r here is like the 3 in the last one. We wanted 3 of the same kind. All right, 3 of a kind. K was the number of different kinds. There were 3 different types of cards. And we wanted to know how many does it take to get 3 of a kind. So what's the minimum cardinality? N. So that's the smallest number of cards. So the set of cards would be my S, such that if we divide S into our k subsets, so there's k coming back again, the number of types, then at least one of these subsets has at least are elements, at least 3 of a kind. And so what is the smallest cardinality in general, and why? Well, the number is this. It's k times r minus 1 plus 1. And so remember, in order for this to be to satisfy the statement, I need this to be the smallest number. So n is the smallest number such that n over k is equal to r. That's what we're really looking for here. And so we can go ahead and prove that this works. So what happens if I take n over k and compute the ceiling of that with this as my n? Well, I would get ceiling of k times r minus 1 plus 1 all over k. Notice I can cancel k out there if I split up my fraction. So this would be ceiling of r minus 1 plus 1 over k. So r minus 1 is an integer. And so if I add 1 over k to that, that'll be some number between 0 and 1. This will bump it up to the next integer. So this is r. And so it satisfies the fact that ceiling of n over k is equal to r, but is it the smallest one? Yeah, it has to be. If it's any smaller, then it's less than k times r minus 1. And the ceiling of k times r minus 1 over k is just r minus 1. And so this is indeed the very smallest one. So that's sort of a hand-wavy proof that this really works. Again, you can refer to the book to see the full details of this worked out, but that is essentially why. So let's see an example of this. So how many people are needed to be sure that at least 2 of them have a birthday during the same month? All right, so I'd like to see this in terms of variables, n, k, and r. So can I identify those things in this problem? All right, so remember r is my number of a kind, how many I want of the same kind. So maybe it'll actually be helpful to figure out what are the different kinds of people here. I have some number of people. That's my big set S. It's a collection of people. And so the different kinds of people, well, the question's asking about how many people have during the same month. So these are my kinds of people. I'll group them based on the month they were born. And so how many months are there? There are 12 months. And so this is really telling me that k should be 12 in the statement of the Pigeonhole Principle. And how many do I want of the same kind? Well, I want 2. So that's my r. And so this is telling me that the smallest number of people I need to have at the party to guarantee 2 of the same kind is n equal, so k, 12, times r minus 1, 2 minus 1 plus 1. And so that's 13. So 13 is the smallest number. If I have 13 people at the party, I'm guaranteed this condition. If I have 12 people at the party, I am not guaranteed. This is indeed the smallest number. Cool. So let's ask yet another variation on this type of question. So I still have this bowl of coins on my desk with at least 10 of each denomination. Let's say I choose 16 coins at random. It follows I'm guaranteed that I'll have at least 4 pennies, at least 6 nickels, at least 2 dimes, or at least 7 quarters. I know that at least one of these things has to happen, 6 nickels, 2 dimes, or 7 quarters. So why? That's what I want to ask. Why is this true? And how can we know that this is true? So let's try it by contrapositive, right? Look at this implication. If I choose 16 coins, then this will happen. So let's assume that this doesn't happen, that none of these things happen. So assume that we have less than 4 pennies, less than 6 nickels, less than 2 dimes, and less than 7 quarters. Since these are all integers, that means we have at most 3 pennies, at most 5 nickels, at most 1 dime, and at most 6 quarters. And so how many how many coins did I grab? Well, if I sum these all up, that should tell me, what's the most number of coins I must have grabbed. So number of coins is less than or equal to 3 plus 5 plus 1 plus 6. So that's 9. That's 15. But I had 16 coins. And that's not 16. And so this is true. We can prove it with that sort of strategy. And so I'd like to be able to do this in general, right? The 4, 6, 2, and 7 weren't super special by themselves, but together, when I added up one less than each of those, I got exactly one less than the number of coins that I grabbed. And that meant, there was a contradiction in that. That must not have been the case, that I had at most those many. And so we'd like to generalize this sort of argument to other cases. So that last example motivates the following more general pigeonhole principle. So if we have a set with n elements partitioned into k pairwise disjoint subsets again, and then we put this restriction on the number of elements in S sub I that has to be greater than or equal to this number n sub I for every positive integer n sub I, then any subset of S with at least this many elements in it must contain at least n sub I elements of S sub I for some integer I. All right, so there's a lot to break down here. My n sub I, these are like the 4 pennies. So like n sub 1 would be 4, the 6 nickels, n sub 2 would be 6, the 2 dimes, n sub 3 would be 2, and so on. So these n sub I are what I want. I want at least one of these for some n sub I. And what this is telling me is how many numbers I need in my big set in order to guarantee this. And so the proof of this is not too bad. We go by contradiction again. I'll just sort of walk through the proof sketch. So we go by contradiction. So that is, we'll assume we have a set A with cardinality at least this much, but it doesn't have the property that we want. So what would it mean to not have the property? Well, that means in A sub I, there is strictly less than n sub I elements for each S sub I. And so what that means then would be that we could count the cardinality of A by adding up these n sub I's, but we know, or by adding up the cardinalities of the S sub I's, but we know that cardinalities of the S sub I is at most one less than each n sub I. So cardinality of A then would be less than or equal to the sum of n sub I minus 1 for each I equals 1 to k. And so what does this give us? Well, we know that this number, so if I subtract 1 from this equation, cardinality of A then would be greater than, cardinality of A minus 1 would be greater than or equal to this sum that we have over on the other equation over here, okay, of n sub I minus 1. So turning this inequality around, I have that this sum is less than or equal to 1 less than the cardinality of A. So this is less than or equal to cardinality of A minus 1. And so pretty clearly that's a contradiction. If you want, you can subtract cardinality of A on both sides of this, and I would get 0 is less than or equal to negative 1, and that's clearly a contradiction. So again, feel free to look at the book for a little more detail on this, but I think this proof sketch is sufficient for illustrating the idea behind the proof, right? If we have less than this, we're gonna get some issue. All right, let's see in the next slide a bit of a stranger example of how we can apply pigeonhole principle. So I present this following example to illustrate that while sometimes a problem doesn't look like it's a pigeonhole problem, we can actually use the pigeonhole principle to solve it. All right, so we have this problem here. We have a graduate student as a mathematics tutor during the semester each day, including the weekends. She tutors for 1-hour periods. She charges $10 per hour. And then here's some crucial piece of information. During the last 20 days of the semester, she tutored a total of 28 hours, and she tutored at least 1 hour every day. And what we want to do is we want to show that there was a certain period of consecutive days when she earned exactly $100. So in my opinion, this doesn't scream pigeonhole principle, because usually Pigeonhole Principle says something like there's at least one day where she earned at least this amount of money, something like that. But this is phrased in terms of exactly, and that there is some, maybe this is a hint that it's Pigeonhole, that there's some period of consecutive days where she earned this. But nevertheless, it's exactly $100, so it's not clear how Pigeonhole will help us here. But nevertheless, it'll come in handy. So let's talk through a solution. So what I'm going to do is I'm going to define some variables. I'm going to keep a running total of how much she's earned during the first I days of these 20 days. So for example, D sub 1, amount of time tutored. So D sub 1 is number of hours tutored during day 1 of the 20 days. So I'm sort of just focusing on these last 20 days. And then D2, like I said, these are going to be running total. So this will be number of hours tutored during the first 2 days. And so on. So in general, D sub I will be the ith running total, the number of hours she tutored during the first I days. So number of hours during first I days. And so I would end, since this is just over 20 days, D sub 20 would be my last one, and that's the total amount of money she earned over the 28, over the last 20 days. So that's D sub 20, and we actually know what D sub 20 is, right? D sub 20 should be 28 because that's what she earned that's the number of hours she worked during these last 20 days. So that's my final running total would be D sub 20. Now, I want to draw attention to this fact that she worked 1 hour each day. What this tells me is that these D sub i's are distinct. So what do I mean by that? Well, I mean that since she tutored at least 1 hour every day, then D sub 1 compared to D sub 20, or D sub 2, it had to go up by at least 1. It could have gone up by more, but she tutored at least 1 hour during the second day, and so that running total must have gone up by at least 1, and so it's strictly bigger than the first running total. And same thing for D3, we have to go up by some amount, and we can continue on. So D sub 18 will be less than D sub 19, and D sub 19 will be less than D sub 20, which we know is 28. And we know she tutored at least 1 hour, so 0 is certainly less than D sub 1 through D sub 20. All right, so now comes sort of a magic trick of how we would think to do this. I'll try and explain how one would come up with this next step. So we want to show she earned exactly $100 for some consecutive days. $100 of work would be 10 hours, would be working for 10 hours, tutoring for 10 hours. And so I'm going to add 10 to each one of these D sub i's. And since each of these are distinct, when I add 10 to this, each of those will be distinct. Actually, let me make a comment here. The D sub i's are distinct. No two are the same. And then the same will happen if I add 10 to everything. So 10 less than D sub 1 plus 10, less than D sub 2 plus 10, and so on. D sub 19 plus 10, less than D sub 20 plus 10, and so that's 38 total there. And again, since I just added 10 to everything, they'll still be distinct. D sub I plus 10, this sequence, this set, are also distinct. Or there are distinct values in the set, no repeats. So, okay, so we have 20 total numbers here. My D sub i's, there's 20 of them, and there's 20 numbers here, 20 different numbers, D sub I plus 10. Well, in each set, they are different from each other. So the D sub I plus 10s are all different from each other, and the D sub i's themselves are all different from each other. So I have a total of 40 numbers, but look at the highest number they can all be is 38. So in total, all of the D sub i's and the D sub i's plus 10, there's 40 of those, but they're all crammed into this interval between 1 and 38. And so what that means is that there has to be at least 2 of these numbers that are the same. Now, We know that the d sub i's themselves can't be the same as another d sub I, so we know d sub I is not equal to d sub j for any pair I and j. And we also know the same thing with the d sub I plus 10s because those are distinct. So d sub I plus 10 is not equal to d sub j plus 10 for any I and j. But nevertheless, the pigeonhole principle tells us that since we have 40 numbers and only 38 possibilities, 2 of these numbers have to be the same. Since none of these numbers can be the same and none of these numbers can be the same, well, we have to have that d sub I is equal to d sub j plus 10 for some I and j. So by pigeonhole principle, d sub I must be equal to d sub j plus 10 for some I and j. All right, so what can we do with that? Well, let's subtract off d sub j from both sides. So we have d sub I minus d sub j is equal to 10. So what this means, now we need to interpret this. D sub I minus D sub j, so D sub I is number of hours worked up to day I, and D sub j is number of hours worked up to day j. And so this would be the number of hours worked between day j and day I. So this is number of hours worked between day j and day I. So that's a period of consecutive days. And how many hours were worked during that period? That period of consecutive days? Well, 10. And so that means this is our solution. And so that means she worked 10 hours, hence earned $100 during day I to during j to day I, during that period of consecutive days. We did it. So that's how we'd figure it out. We'd figure out which of these were doubled up, and then we'd subtract them, and that would tell us the period of days where she earned $100. All right, so it's pretty cool. We needed to sort of invent some variables and do some funny things like add 10 to them, but eventually we got down to our answer using pigeonhole principle. All right, that's it.